the same here, multiplied it by 4, gone to 400. I'm going to switch this to 40, just because it works with some of the CAD files that we already have. And then to get from 400 to 500, we need to multiply it yet again. We'll make this 32, and that should make our final speed 500. I messed around with this a little bit, so doesn't work quite there. Now, obviously, you can use whatever diameter you want. In any of these, you can build your own gear trains. The important thing to remember is, well, there's a couple. The important things to remember is that when you go from a larger gear to a smaller gear, the speed goes up. When you go from a smaller gear to a larger gear, the speed goes down. It's an inverse relation.
I have a quick question. How did you get 30, how did you get to 32 for the diameter for the very last one?
So we know
Like, why
that
did you
we
choose
have
that?
400, so we need to multiply it by 1.25. So 40 divided by 32 would be 1.25. It's just the ratio between them flipped.
Oh, so you're doing like what to do to 400 to get to 500 and then apply that on the.
Exactly.
I see.
Exactly. Because we know that our ending point has to be 500, and we know that our beginning point has to be 200. You could completely flip a lot of these, and they would still make sense in terms of the gear ratio. I just came up with this particular orientation because it's what we've CAD'd for. So this will help you follow along with the CAD. I'll give everybody a quick second to catch up with this, figure out your own sheet, and then I'll move on to our next component. So our next component here is going to be opening up geartrain metric.iam. Should look something like this. That should be in your provided zip folder. If you find it hard to open, it's probably because some of the files from the zip folder have not been extracted properly. Make sure that they've all been extracted to the same folder so that they can interact with each other and they know where to find all of their components. So here we have the base for our gear train, but we don't know exactly what the spacing of all of these axles are. So we want to make sure that they're correct to what we have in our Excel spreadsheet here, all of our center distances. So I'm going to select our gear base here, and I'm going to open it up like this. So now we have just this. Cool. If we want to change where each of these holes is located, we can go into the hole feature on the left here, open it up, and edit our sketch. Now, you can probably see from your, no, you can definitely see from your worksheet. I believe it is page 4 or 5, page 4, what all of the correct numbers should be here, because we're trying to find the distance between each of these, and those center distances should correlate to what we have on our Excel spreadsheet. So the distance between the first and the second axle should be 54 millimeters. Here it's only 50, so we'll edit that. Just double click on it, switch it to 54. The next two gears are axially connected, but the center distances between these two gears should be 40. Right here, we see that it's 50 instead of 40, so we're going to switch that. And then the last one should be 36 millimeters in distance. This is quite a bit off, so we'll change it to 36. So now all of our measurements line up with what we have in our Excel spreadsheet. Does anybody have any questions about what I've done here so far. You'll have to just shout them out. Actually, wait a second. Yeah, I can move this over. There we go. Sorry, I couldn't see y'all for a second. Okay. So, if I finish this sketch, it moves everything around. And then if I close this and I'm going to reopen it, it will have updated everything that I wanted to change. Update the assembly. Yes. There we go. So everything's been changed around so it will be reflective of our gear train. So now that we've adjusted that, we're going to start generating our gears. To start generating gears, you want to go to your design tool up here.
Sorry, how do you update the assembly? I think I missed that. Sorry.
There's a couple different ways you can do it. The easiest is just closing the .iam file and then reopening it, and it'll give you the option to update. You just select yes, and then it will update where all of the holes and all of the axles are.
Oh, okay, thank you.
Just make sure that you save the IPT file first, because if you don't, it won't know to update.
Okay. Yeah, and there's a confirmation box, right? It's supposed to be a confirmation box? Yeah. Okay.
There should be a confirmation box.
All right.
Okay. So now we'll start generating our gears. You've probably done a lot of work with gears, whether you're in 1P10 or 1P13, but you can actually generate gears fairly automatically if we go into our design area here, click on spur gears. We get this big old box. There's a lot of values here. Try to do exactly what I do or exactly what it says on your handout. So first gear, number of teeth. From the Excel spreadsheet, it should be 90. Module should be 1. Face width should be 10. Gear ratio, we want that to not be 0.8, so we'll have to change the number of teeth over here. We'll change the number of teeth over here to 18. Just remember, we want to multiply the speed by 5 here. So 18. Face width should also be 10. No unit correction. Pressure angle should be 20. Okay, so let's calculate. Some of the other values will adjust. And now we want to make sure that we select the 2 axles that we actually want these gears to generate on. So I'll select cylindrical face. Here, that's where we want our first gear. Cylindrical face on the second gear. Select our second axle. Now when I click OK, it'll probably give me a couple error boxes. You just want to click yes to all and everything. And it should generate our 90-degree gear on our first axle and our 90-tooth gear on our first axle and 18-tooth gear on our second axle. Click OK, OK, accept. There we go. Ta-da. 2 perfectly working gears that rotate and mesh with each other. Couple things we should notice here. They still slide on their axle, so they're not constrained in that direction. And if we move our axles around, the gears don't rotate with them. So that's a problem. So what we're going to do is we are going to take our constraints and we're going to give them a couple knocks around, make sure that they know exactly where they're supposed to be. So I'm going to select this wall and this side of the gear, and we're going to give them 100mm offset, and I'm going to apply that. So now they won't slide along the axle at all, but they'll rotate in place. So that only leaves us with 1 degree of issue, I guess, which is that this rotates separately from the gear. Now, how do we want to change that? Because there's not really any immediately obvious surfaces that we can use to constrain the axis of rotation with this axis so that they rotate together. So what we're going to do is we're actually going to go into the rods here. We're going to go into their origin, and we're going to select one of their origin planes. I'm going to turn on the visibility. And I'm going to do the same thing for our gear right here. Go all the way down into the origin, and then you'll select one of the origin planes and make it visible. And then, now that we have these two origin planes, we can actually constrain those to each other. And that will make sure that they always rotate in a synchronized manner. Constrain, it's a simple mate-to-mate constraint. Apply that. And now we see, when we rotate the crankshaft here, the gears rotate with it. Of course, we have to do the same with this gear over here, otherwise this axle isn't going to turn. So I'm going to close up that gear, open our second gear, open up its origin, make its origin planes visible. And then I can constrain those. Great, now everything turns perfectly. Now we just have to do that a couple more times for our other areas, and we should be fine. So, back to our design tab. I guess I should ask if any questions or issues, please drop it in the main channels, and either Adrian or Val will be able to come and help you and
Could
give you a
you
little bit.
could you go over
Yep.
the directed angle constraints again? I missed that part where like which space to constrain.
Oh, so that the axles rotate with the gears?
Yeah.
Of course. So how you do that is you have to make sure that an origin plane for both of the bodies is visible. So for a gear, you'd go into the spur gear tab, you'd go into the spur gear 1 or spur gear 2, open that up, open up its origin planes, and then make them visible by right-clicking and selecting visibility. You want to do that for the gear, and then you also want to do that for the rods. Open up the origin, make their origin plane visible. After you have them visible, it's fairly easy. You just have to use your constraint tool and then a mate-to-mate constraint between both of the planes. And then that should work. Does that make sense?
And yeah, we do it for both rods, right?
Yes, both rods. Because if you weren't to do it, the other rod won't rotate.
Right.
So we'll continue onwards with this by adding some more gears. So instead of 90 to 18, we are now moving from 64 to 16. So we'll change the number of teeth to reflect that. 64 to 16. Hit calculate there. All of the face width and everything, that's all the same. Our first gear is going to be on this axle, and our second gear is going to be on this axle. And this should create the second level of our gear train. Accept all of that. There we go. So we have the same issue with these that we did initially with our other gears, which is that they slide around and they don't rotate with our axles. Much the same as we did with our first two. Mate constraint with an offset to make sure that they don't slide. It's not going to be 100 this time because we don't want them to interfere with each other. So we're just going to say, let's say 60. And then to make them rotate with the axles, going to go into our second set of spur gears. Make their origin planes visible. Do that for both of them. And then we'll do our regular mate constraints. So this gets a little bit weird to look at. So you have to make sure that you're constraining the right axes and everything. So I'll start with the bigger gear. And it's given axle. There we go. And then we can move on to our smaller gear. And it's given axle. So I'm going to turn the crankshaft, make sure that everything rotates together. As you can see, it does. So that leaves us with one level of gears to add on. I'll give people another second to catch up. I admire y'all actually showing up to this. The dedication to extra credit or to learning more about CAD, whichever you're doing this for, is very admirable. I would definitely have been studying for a physics test if I were you. So y'all are better students than I am. That is for damn sure. All right, I will start our third level here. Going back to our Excel spreadsheet, we're going from 40 to 32. The final small adjustment to get from 400 RPM to 500 RPM. So our first gear, 40 teeth. Second gear, 32. Our first gear is going to be on this axle, and our second gear is going to be on this axle. Accept everything, and there we go. Same issues yet again, so we are going to constrain them as we have the others. Mate to mate constraint with a 30 millimeter offset. And then we have to do the same axle chicanery as we've already done. So I will close our spur gears 2 and open our spur gears 3. Origin of the first one, make the YZ plane visible. Doesn't have to be the YZ plane, but it's fairly easy since it's the first one that pops up. Same thing with spur gear 2 here. And then a mate to mate constraint for all of those. And now we double check that everything is going well. I'm going to turn this crankshaft, and if we see rotation on the final axle, we know that everything is working as intended. Wow, look at that. It's almost like I did this 2 or 3 times yesterday to make sure I didn't mess it up in this workshop. Fantastic. So does anybody have any parts of that they'd like me to go over again? Because I would be more than happy to.
Yeah, could you go over how you made this second set of spur gears, please?
The second set?
Yeah.
Okay, yeah, for sure. So I'll just make a second set on the same axles just to make it easier. So I started based off of our second set of 2 gears, so 64 teeth or 64 in diameter and 16 in diameter. Go to the Design tab, spur gear tool, adjust the number of teeth, 64 and 16. Now you can calculate and all of the different numbers will adjust, or you can just start selecting where you want to generate them. That part doesn't really matter too much. But what we're going to do is we're going to select the 2 axles that we want to generate our gears on. I'll click cylindrical face here and select the second rod in the train. And the second cylindrical face will be the third axle in the train. Select OK, OK again, and accept. And there we go. We have another second level of gears that we've created there. And then we do the same process of making YZ planes visible and then constraining them to the axles to make sure that they rotate in unison. And then we do a mate-to-mate constraint on one of the faces with another face, and then we control the offset. Does that make sense?
Yeah, thank you.
Awesome. Any other parts of this that people would want me to go over? More than happy to do it. This lab is not going to run very long. I mean,
Is there a particular like offset to the wall for the last set of gears?
Not at all.
Okay.
No. As long as there is an offset and it's not just kind of sliding around, you're good.
Okay.
Yeah, and at this point, for the submission, I posted something in announcements, and if you guys want to just save an STL file of your assembly here, you can submit that. And the next parts will be going over some cool simulation stuff.
Yeah, if you've ever wondered about how to get videos of your assemblies in action moving around, that's what we're going to be working on next. So I think I'll give people about how long do you think, Adrian? How long do you think I should give just to let people work on this for a little? Or Val?
I say give him like 15 minutes.
15 minutes?
Yeah, if we're not in the big rush.
Yeah, I don't. We really aren't. Let's say 5 minutes. Just because I don't want to keep people here unnecessarily because, physics. At 7:35, I'm gonna mute myself until 7:35 and then I'll pop back on and we'll get started talking about animation and how to get videos of everything and how to make exploded diagrams. So I will talk to you all in about 5 minutes. I'm going to leave this image up just to show you what it should look like once you're done.
So what are the requirements for the submission? Is it just the gear train to work?
It's just an STL file of the completed gear train.
Yeah. So the STL file is just like a really generic 3D model file. So like, even if the constraints don't work fully, but you have gears there, then that's okay.
Okay.
Just out of curiosity, while we're all just kind of like mumbling around, do you guys have like a gear-related final project for your 1P13 or 1P10 this year?
Like potentially, yeah, I think so. Like we're doing like the client stuff. Like we're making a device for like a specific client.
Right.
Like our design may or may not have gears. Yeah.
Right. I guess that's a result of the amalgamation of all the design courses that they did last year, I don't know. But a lot of our the first year courses used to be split up to like computing, and then there was one that was focused on CAD stuff like this and gears, and then there was another one where you worked with the client. So we actually had 2 projects that year, where there's one we had to just do something similar to the spreadsheet given here, where we were given an input speed and output speed and design a gear train for that.
Yeah, that was a lab, I think, for us. Now we're just doing.
Okay.
Yeah, we're just doing like projects.
That's pretty nice. Yeah, in my opinion, there should only be 1 project per semester.
Yeah, that's a good idea.
And the projects, every year, you'll have like a big project, pretty much. I mean, this is me speaking from experience in mechanical, but like each project every year gets more intensive incrementally. Until in 4th year when you have capstone and you're like dying from it. But it's all fun. Also, at this point, if anyone needs to go back and see something that Aiden did earlier and they just want to see it again, this is currently being streamed on our YouTube channel. So just search up McMaster Design League on YouTube and should be like the first result. And it's just look for the live session right now. It should be called Workshop Number 6. And on YouTube, it's nice that it lets you go back and stuff. And yeah, that's also where the recording will be after this workshop.
All right. Hopefully people are ready to continue with this. So we should be on page 7 or 8, I believe, of the handout. The simulation and animations / explosions section. So now there's a couple different ways that we can go about actually moving this around and recording it. The one common way is creating a full dynamic simulation. It's a little bit complicated. We're not going to do that right now. What's a lot easier is just to create all of these constraints and then drive the assembly. So that's what we're going to do. First step to doing that, sorry, just dealing with some stuff on my side here.
Sorry, before we move on, the submission, does it include the animation stuff too, or?
No, it does not.
Yeah, in that case, I think I'll go. Thanks for the workshops, guys.
Well, thank you for coming to them. Enjoy the rest of your night, and good luck on physics.
Yeah, we'll need it.
You're going to do great. Just stay calm, get those part marks. Okay, so I'm going to open up my crank here, and I'm going to make its origin visible as well, like I have before. I'm not going to use the YZ plane. I'm actually going to use the XZ plane You'll see why I want to do that in a little bit. So I'm going to constrain this plane that I've made using an angle constraint. And I'm going to select origin plane and this plane over here. And make sure that it's a directed angle. And I'm just going to leave it at 0 degrees, and I'll apply that. So now that's fully constrained. I can look over here on my sidebar, and I can see the constraint. And I'm going to right click it. Now I can select drive. And we see this nice little box up here that we can use to control the motion of this constraint. So we're going to start at 0 degrees. And since we want it to kind of show stuff off, I'm going to go with what the handout prescribes, which I believe is 720 degrees of rotation. So I'll say 720. I'm not going to have any pause delay. And then I want to record this. So let's record. I'll just have it as a workshop video. Save that. We'll go custom. Let's do 1200 by 800. It's really just sizing. You don't have to do anything specific, but 1200 by 800 is pretty easy. And now I'm recording and I'm going to press play. And you see it's going to rotate until it goes all the way through 720 degrees. We don't necessarily need to sit here and watch it the entire time, but once it is complete, we will receive our video. I'm going to zoom in. And that's the beauty of gear trains. You can turn relatively slow motion into very, very fast motion very, very quickly. Gearboxes are fun. Okay. So that's lovely. And now we're going to move on to how to create an exploded assembly drawing. So we're going to start that off by creating a new file. We'll go to File, New, and you've probably all dealt with parts, assemblies, and drawings in all of your courses by this point, but you might not have done any presentations. So we'll go to standard millimeter.ipn. We'll create a new project file there. I'm going to choose gear train metric. All right. So now that we've created that, what we want to do is we want to tweak it so that all of these parts are separated, so that anybody looking at it will be able to see all of the individual components. How am I going to do that? We'll take this button up here, tweak components. I'll select the component that I want to move, and then I can move it wherever I want. I think based off of this orientation, it would be easiest to slide everything out to the side, like so, just by whatever amount. Cool. Just move everything over. That's a little bit of trouble there, but just got to select it. Gears that are still in mesh connection, I'm going to try to make them stay in mesh connection. There we go. And okay, so that should be relatively exploded. Now, if we look down here, we actually see a little bit of a timeline, and each of these tweaks that I've done is about 2.5 seconds, as you can see. So that means that if I were to bring this back to the beginning of our exploding process and hit play, I can see all of the different parts slide out from the main housing. Beautiful. And now if we want to get a snapshot of what the fully exploded assembly looks like, we can drag our little indicator here all the way to the end of the exploding process, and we're going to hit New Snapshot View. Here we have our new snapshot. I'll right-click it, and let's create a drawing. Save the document. Let's say gear train metric exploded diagram. Yes to all. Okay. Make sure that you pick ANSI millimeter. Pick any of the other ones, things may get weird. And let's just use a random template. Just a completely normal template. That is going to generate a drawing for us. So the scale is a little off. That's looking a little small. Let's go 1 to 2. Still looking a little small. Let's just say normal scale. I'll move this to the center. Awesome. So I think I've hit a pretty normal point to ask again. Is there anything that I have done thus far that people have found confusing that you'd want me to do again? Don't be shy. I don't bite. I mean, like food, of course, but like not in the metaphorical sense. All right, sweet. In that case, we'll keep moving on. We should be on which page of the handout? We should be on about page 16 now, if you're following along. What we're going to do is we are now going to create some balloons in order to mark all of the parts that we've created. So we'll go to the Annotate tab up here, go to our Balloon tool, and Auto Balloon. So what we want to do with our Auto Balloon tool is we will just click a random point here, or will we? Wait a second. Oh, yeah, sorry, of course. Took me a second there. Okay, select the view. No, I did it yesterday. I just completely forgot. Okay, so after you've clicked your view, because you haven't forgotten it like me, you'll select any point and drag across and try to encapsulate all of the parts. Now you see I missed a tiny corner of that, so I'll have to try again. And there we go. Now we've selected everything. So let's select placement. And I think this is a pretty normal place to put it just because there's going to be arrows going off from each of those numbers to the different parts. And we want to make sure that they'll be relatively clear. There we go. Awesome. So now if we zoom in here, we can see each of these parts is labeled. What do these labels actually mean? Now we just have a bunch of numbers and arrows. Is that actually useful? Not really. So what we need to create is we need to create a parts list or a bill of materials. So we are going to go up here to parts list. And we can select here. Okay. And we can put this wherever we want. I'm going to put it up in this corner because I think that that is far enough away from other things. And it has a description of what each of the items are that are indicated by the balloons. Okay, so now we have the exploded diagram. Now we're mostly worried about aesthetic things. Can anybody tell me what a problem with this might be? Because there's a couple and they're pretty glaring. All right, I can answer my own question. It's hard to read. All of the text is really small, and the object in the middle is really big. It's kind of not great. So what we can do is we can actually go over here to the left, and we can edit our sheet. And we can change the size. Let's go to size C. This is a little big now. Move this around a little bit. We can move all the balloons and everything. Okay, I think that may have been a mistake. But either way, that's something that you can do to edit all of the sheet elements. Let's try something else. Edit sheet. Right. Da, 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 da. Oh, sorry. It's been a minute. Oh. Did not mean to do that one. There we go. Okay. Now that I've finally remembered how to use Inventor, drag this over here. Bring this back in. Okay. Now that's quite a bit easier to read, simply because we can actually see the text from a normal distance away. There's obviously a lot of other things that you can do with Edit Sheet. You can change stuff to do with what is in your title block. You can add little touches here and there, but that is the basics. Anything that anybody would like me to go back over that I've done in the past 20 minutes? Or really anything today? Because otherwise, that's just about everything for today. Oh no, wait. iProperties. We can go to the left side of our window here. Gear train metric. Exploded diagram. iProperties. And we can change all of our title, subject, author, everything. I'm not going to. So that is the Gear Trains and Animations workshop. I don't want to take up too much more of your time just because I know physics is looming and ever present. But does anybody have any questions about this, stream selection, really anything? I'll just kind of open the floor for the last little bit because this is kind of a short workshop.